This afternoon, our speaker for our session will be JGunn from IRFM CA, who will present to us, bring us back to our experiment and show us experimental results from the West tokamak concerning the ion temperature in the downhole.
Thanks, Patrick. So this is a purely experimental talk with some new results that we got this winter. And it was Guillaume's idea that I present them to you because the results, as you'll see, are a bit unexpected and difficult to explain. So what we're going to be talking about are new measurements of the ion temperature that were made in the West tokamak. This is a collaboration with the Bulgarian Academy of Sciences, who built for us this instrument called the retarding field analyzer that we use to measure the ion temperature. And we have a picture of it here on the right, sticking up above the diverter, and I'll explain a bit how it works. How does this work here? Oh, yeah, okay. So I have to stay there near the mic, I guess. Yeah. Okay. So we're gonna drink a lot of water. I nearly passed out on the way here. And very hot today. So we're going to start by discussing the operational principle of the retarding field analyzer, show some photos of it and its installation, and give a brief description of how the magnetically driven drive system works, because it's a mobile system, which is normally hiding below the diverter, and then we stick it up briefly in the diverter plasma to make measurements. I'll show recent measurements of the ion temperature from the campaign 11, so the 11th experimental campaign at West, and these were carried out in February of this year. And then we'll look at the correlation of ion and electron temperatures with diverter regimes. The ion temperature is important. The ions impact the diverter and cause sputtering, and we need to know with what energy they strike the diverter in order to aid our understanding of sputtering mechanisms and so on. It's also important in atomic physics processes. And it's an important issue, and especially what concerns the lifetime of the diverters in future fusion reactors. Now, ion temperature also affects the interpretation of simple Langmuir probes. A Langmuir probe is basically a voltmeter that you stick into the plasma to measure its electron temperature and density, but it also depends on the ion temperature. And we usually just make assumptions on the ion temperature because it's actually almost never measured. So a Langmuir probe can only measure the electron temperature and the ion particle flux, and we'll talk a bit about that. For example, we assume that the ion temperature is equal to the electron temperature at the diverter. That's a standard practice. It comes kind of our, say, intuition with two-point modeling and so on. Scrape up layer, but there's actually no justification to make this assumption. We just make it because we have no measurements. So, and it's easy to make an assumption. Now here's the operational principle of the retarding field analyzer. It consists of some very fine metallic elements that are stacked up together. And the goal of the device is to repel the electrons that come in from the plasma, leaving only the ions to be analyzed inside of the cavity. Now, facing the plasma on the left here, we have a slit plate, which is, the slit has to be very small. It has to be not much bigger than the Debye length of the plasma. So in fact, it's laser cut in a thin nickel or stainless steel plate. The plate is 100 micrometers thick, and the slit itself is 30 micrometers wide, which is about the order of the Debye length in West diverter plasmas. So naturally, in front of this slit plate, you have a Debye sheaf, which forms as it does in front of any piece of metal in a tokamak. And the Debye sheaf has a potential drop in it of magnitude V sheaf, Vs on the diagram. And it pushes back most of the electrons into the plasma because they can't overcome the electric potential. A few of them do make it through, and we have to handle them once they get inside. All the ions do come through, and then once they're inside the cavity, we can repel them as a function of their energy. So the grid number 1 that you see here, we vary its voltage from 0 volts which allows all the ions to go through and be collected. So that gives us a measure of the ion flux striking the slit plate. And then we can scan it positively up to several hundred volts in order to gradually push back the ions as a function of their energies. Now, the ions can also hit the second grid, and electrons that come into the cavity can also hit it. So we bias the second grid negatively. It's the most negative voltage in the system in order to push back the remaining electrons and also repel any secondary electrons that get released from the collector due to ion impact. And the collector itself is electrically grounded, and we just measure the current. The currents are of the order of tens of microamps. So we need rather special electronics to get these signals that come over very long cables from the tokamak down into the diagnostic room. We transmit the signals actually by fiber optics. Now here's some photos. And we see some of the interior elements of the retarding field analyzer. We're very limited in volume with this thing because, as you may know, the West diverter is composed of actively cooled tungsten plasma-facing units, which are very tightly adjusted. And they typically have 0.5 millimeter spacing between them, so it doesn't leave much room to install a probe. So we had to cut some of these PFUs a little bit wider than normally. So we have slits of about, if I remember correctly, 6 millimeters between the PFUs. So our probe had to be no more than 4 millimeters thick. So this was quite a challenge for our technical staff. Now these are some pictures of, you can see one of the grids here down below, and I've zoomed on it. This was laser cut in Bulgaria by a very good young company. We were very happy with the results because we had to design this, of course, in a CAD model, and they fed it into the CAD model, and the laser cut everything out just absolutely perfectly. It's just stunning to see. Now, unfortunately, I'll probably finish with that. We ended up destroying this probe nonetheless in a disruption, and we have to build a new one this summer. But fortunately, we have some spare parts. Now some photos. We see here the retarding field analyzer sticking up above the diverter in its measuring position. Normally it's sitting 3 millimeters below the trailing edges of these tungsten blocks that you see here. We call these tungsten monoblocks. They're actively cooled. There are cooling pipes in them running from left to right in this image. You can see that the slit between these front two blocks, these row of blocks is, as I said, larger than all the other slits. The ones that you see running kind of into the page are 0.5 millimeters wide. And then there's an oval hole on the probe, and behind this hole is the slit plate. It's hard to see in the picture. And then behind it we have mica insulators stacked up with all the different grids, and finally the collector. So this is really the business end of the probe that receives all the fluxes coming from the plasma. Now it has to move in and out very quickly because being only 100 micrometers thick, the slit plate would be vaporized if we left it too long. So I'm going to talk about the drive system. Now the slit plate itself, when it's up inside the plasma, is 1 millimeter above the target. So we're measuring 1 millimeter above the, let's say, the sheath region of the diverter target. And we can actually see when the thing is going up, the variation of fluxes inside the Debye sheath, which is itself really interesting. We're looking forward to analyzing that in detail. Now here's a picture looking from the top. You can see how it's installed in the machine. There's lots of things to look at here. It's actually a modular system which is mounted on a magnetically driven drive that you can't see in this picture, but I'll show on the next slide what it looked like before we installed it under the diverter. And it has like we call it a stirrup or a fork on which you can bolt different kinds of probes. And these are what they call the vis imperdables, how do you say that? Unloosable screws, so we don't drop them into the tokamak if we're, shaking or sweaty or something. So we actually had another probe mounted here for the last couple of years, and we installed this one last autumn. Our technician went in, unbolted the probe that was there, and then put this one in. Well, the blocks themselves are interesting to look at. They're beveled. They have to be beveled in the toroidal direction because the fluxes of particles and energy are coming down to the diverter at glancing angles of incidence. So typically between 1 and 3 degrees in west. So practically parallel to the surface. So any block that has a sharp edge, due to assembly tolerances, will be blasted by this flux, and the leading edges can melt, and they do sometimes. So all the blocks are beveled by 1 degree in the toroidal direction to protect the leading edges. And so at the left edge of each tile, you see lots of deposits, because this is a cold region, which is shadowed magnetically by the block preceding it. And so stuff can be deposited on these blocks. It's conducting mostly. It's made of tungsten, oxygen, boron, anything that's in the machine ends up in these layers, in these cold areas that are protected from the plasma. Now the probe itself, I haven't seen it yet, but my technician removed it from the machine a week or two ago, and apparently it also has some deposits on it. But we're gonna see that soon. This week, I hope. So here's how the thing works. So as I said, we make very brief expositions of the retarding field analyzer, thanks to a system we call the mousetrap. And there's a picture of 2 different kinds of mousetraps. We have 6 of them in total on the lower diverter with different kinds of Langmuir probes. You can see on the one on the left here, a system that we call the pop-up probe system. There's 10 individual pins that pop up into the plasma and measure electron temperature and ion flux. Excuse me. And this is the other probe that was installed in the tokamak before the retarding field analyzer. Now, how it works is the back part here. There's a bar here, which is bolted onto the stainless steel support structure of the diverter, and onto which itself are bolted the actively cooled plasma phasing units. We only had 16 millimeters available to make this system, because there's only 16 millimeters below the bottom of the monoblocks and the support plate. So this took a lot of design work also, and we did a lot of it in collaboration with Chinese colleagues who gave us a lot of help with this. So how it works is you have a coil. You can see the coil in white, which has, in this case, 36 turns with a cross section of it's a diameter of about 10 centimeters. And when we put a current in the coil, the lens force makes it want to move to align the magnetic moment with the toroidal magnetic field. And it's designed to make a vertical movement. Oh, it's a 2-degree rotation, which leads, given the lever arm here, which is about 15 centimeters, to a vertical movement of 5 millimeters. The probe is usually 4 to 3 millimeters below the surface. And when we put it in action, it can come up to 1 or 2 millimeters above the surface. And this is what makes it work. So here's some curves on the left. We have the voltage that we apply to the coil. Yeah. You see something?
We don't see anything. There's my glasses.
That's jumpy. I don't know how to do the.
I just pointed.
Okay. They won't see this on Zoom, will they?
So.
Might be what? So?
Your mouse. You don't see it.
It's a mouse.
It's pointer.
It's jumpy. It's there, but it's kind of jumpy.
But what?
Isn't it possible to have like a laser thing? Point the option.
Yeah.
How's that? Okay. This here. Oh. So, okay. So this is a shot, data from one particular discharge in west, 60,998. And we've made 3 movements of the probe into the plasma, once every 2 seconds. The procedure is to apply a negative voltage to the coil a few hundred milliseconds before the desired measurement time, in order to kind of drive it down onto the diverter and define a reference position. We call this thing the mousetrap, because it looks like a mousetrap to us. There's a spring that you can see here on this axis, which brings the probe back down in case we lose the power to the coil, or something goes wrong with the computer program. There's at least this spring that brings the probe down below the diverter. That's why we call it the mousetrap. And then this also allows us to measure the resistance of the coil, which we need to recalculate the velocity due to the induced current in the coil. We don't have an actual physical measurement of the position of the probe, like with the laser or anything like that. So we measure the theoretical current that should be flowing in the coil if it's not moving and if there's no magnetic field. You can see that there's a curve, I think it's probably blue here, which is a regular triangle. But then there's a second curve, which is pink, I guess, which it looks different than the theoretical curve that let's say the voltage that we're asking for, because there's a back EMF, of course, as the probe moves. And if we take the difference between the theoretical current and the real current that we measure, we obtain the induced current, which is down here. And this is proportional directly to the velocity of the probe in linear velocity after some transformations. So we integrate it in time, and this gives us the position. So you can see here the position of 3 of the different probes, which move simultaneously. And the stroke length is, as we hoped it would be, about 5 millimeters. We have an error bar of about maybe, let's say, 5 to 10% on this reconstruction due to noise in the circuit. MHD modes that we pick up very well, by the way, with these coils. And so this gives an idea of how the thing works. Now some measurements. Now this is one of the earlier shots from the campaign, and it's kind of a funny story, because in the beginning we were always measuring about 50 electron volts all the time, whether it was ohmic plasma or heated plasmas. And I was actually starting to get a little bit worried, because this doesn't seem right. It always measures the same thing. But this is what it gave. This is showing a shot. On the right are some of the plasma parameters. This is a shot with 400 kiloamperes of plasma current. And the dots represent the times at which we made measurements with this retarding field analyzer. This is the line average density going through the core of the plasma in red. So we're up to about 2.4 times 10 to the 19 per meter squared. Per meter squared because it's a line average density. And then finally, we have the density in the lower diverter going through the X point. There's an interferometer cord very close to the diverter. And here we have in black, the ohmic power injected into the plasma. There was no additional heating power on this shot, and the radiated power. And you can see that we're at about 100% radiation in this shot. So the plasma is very dirty, and it should be very cold. But we measure. The blue curve on the left here is the electron temperature measured by a Langmuir probe, which is at the same radial position on the diverter as the RFA. So we have about 15 electron volts, let's say. And the ion temperature is about 50 electron volts. This is very surprising, because the plasma, we have the feeling that it should be dense enough to have equipartition as the ions and electrons come down to the diverter. So it's a bit surprising to have such a high ion temperature. And I think we'll be able to discuss afterwards with the modelers on what they expect and why this is so surprising to them. But, as an experimentalist, we're honest, and we say maybe we're just making a mistake. So we tried things like varying the sweep frequency, to see if there's any problem with bandpass in the circuits. We couldn't find anything that seemed to be wrong.
Sorry.
Yes.
Do you trust the electron temperature excursions?
No, here at the end and the beginning, these are, let's say, anomalous. It's just because the signal is so small. The X point forms at 2 seconds. And so actually the particle flux is very, very, very tiny. It's the limit of detection. So when I try to fit this data, it's a cloud of points, and it gives basically garbage. Yeah? What one will do in a publication, of course, is to remove these points and put error bars where they should be, and so on. This is really the raw data from the control room. And then at the end of the shot, of course, the reverse happens. The X point disappears and the flux to the diverter drops very fast and it becomes very difficult to measure anything. Okay. So, which is weirder, high in temperature in ohmic discharges with no heating, or the invariance of both Ti and Te with heating? This is a discharge where we have, again, so it's a bit higher plasma current, 500 kiloamps. Again, we make three measurements with the system. Density is a bit higher, 310⁻⁹. So one might expect the temperature to be a bit lower. But this one has a lower hybrid heating power in blue here. And you can see that the first measurement we made was just before the power came up. There's a little maybe 100 kilowatts of power at the beginning. This is in megawatts, by the way, the units, which they always have to apply with these antennas. It's kind of like a little, they call it the talon, it's a little, the kick maybe to get the thing started, to do a little outgassing before things heat up. I'm not really sure why they have to do this, but the power is essentially zero from the point of view of the ohmic power and the radiated power and so on. And then we make two measurements when the power is at full magnitude. So looks like 1.8 megawatts in this particular shot. The electron temperature. So the power comes on at about 4.5 seconds, just after the first blue dot. You can see that the electron temperature, in this case, doesn't seem to respond at all to the power. Yeah, there's the third dot there. So we're always still about 12 to 15 electron volts. And the ion temperature behaves the same way. So it's the same. There's 55 electron volts when we're still in the ohmic phase, and it doesn't change much with the heating power. So that's why we ask which is weirder. And the text here is the comment in the online session leader handbook. We always write a comment after each discharge, and this might be Patrick's style. I don't know who is the LH coupling not very nice and disruption during plasma current ramp down. So you can see that the lower, they wanted more power actually than we asked for. You can see it's kind of choppy here because there's real-time security loops that are perhaps seeing that a cooling pipe is overheating and they have to reduce a bit the power to prevent overheating. Or it could be copper emission from the plasma, which is also used as a security. If we start seeing too much copper in the plasma, and since the lower hybrid waveguides are made of copper, this means that there's something wrong in the antenna, like maybe an arc, and so they'll cut the power off there also. So this could be due to either of those things. This is the real life in a talk I'm at. Now, yes. So the ion temperature and the electron temperature during the startup phase of the discharge are strongly correlated with the control room definition of what we call detachment. Now, in the early phases of a discharge, if there's too much, let's say, tungsten in the core plasma or some other impurities, it's difficult to get the core electron temperature above what is needed to be, let's say, resistant to tungsten radiation. If we're below 1 or 2 kilo electron volts, then the plasma is prone to MHD instabilities, and we can't get the temperature very high. And you see that on the probe data, on both probes. For this particular shot, again, it's a lower hybrid heated discharge with 500 kiloamps of plasma current. Again, the densities are similar as the previous shots. Power comes on at starting at 4 seconds. So we have one measurement before the power comes on when we're still in the ohmic phase, but with the X point already formed. As I said, it forms around 2 seconds. And we can see that the electron temperature remains very, very low during this phase. On the previous shot, if I remember correctly, it was higher. You see this? This plasma is what we call attached. So it means that we had less MHD probably, perhaps, and higher core electron temperature, even in the ohmic phase. And on this shot, now we can see that the electrons remain cold the whole time until the power comes on. And then we reattach, luckily, because it doesn't always work. And we see that the ion temperature is very low also. It's about the same as the electron temperature. It looks like here maybe 7 or 8 electron volts, while the electron temperature is about 5 electron volts. So this is, I think, one of the first shots where we saw this, and it made us very happy because it meant that we can measure low temperatures if they exist. So we start to believe that these high temperatures are real now. And we're also glad to see that different measurements can arise. And here we have even higher ion temperatures later, last phase at the third movement here, the third measurement. We can see we go up above 70 electron volts in this particular case. Now we have not yet done a lot of detailed systematic correlation analysis to see when is the ion temperature high, when is it low. But just our experience in the control room, after we look at the data from every shot, we're sitting there all day basically, and we look at the data after every shot. We have the impression that the ion temperature is higher when there's a lot of MHD. Is it because the confinement is worse and the energy is escaping faster? This can be discussed. But it's a feeling we have. When you have bad MHD, the ion temperature tends to go up, and the electron temperature doesn't change very much. And what did the session leader say? Still bad coupling and disruption during lower hybrid ramp down. Plasma strongly detached at the startup. And you can see that the ohmic power increased by 50% and the radiated power by 70% with respect to the previous shot. So these are all symptoms of what we call detachment. Here we go. Will these movies work? This definition actually just comes from us watching the television screens when there's a shot. This is where the word detachment comes from. It's not, we don't know if it's really detached, but it looks detached. And we'll see if this works. It should work because it's on the USB key, but it's not working. Okay. That's why I put it on the USB. But you didn't copy the films, maybe. Oh no, you should have.
You should switch from laser to maybe that's because you're on the lasers.
Unselect. Very good. Bravo. Theorie helps. So, okay, here we go. So this is an attached plasma. You can see two. Now I don't have my laser pointer, but I was very clever here. I actually stopped the film when I wanted it to. I forgot that I had done that. So you can see two bright strike regions on the diverter. This is where the plasma interaction is occurring at the high field side, excuse me, and the low field side strike points. And then the next film is what we call detached. Two consecutive shots. So you can see now that there's this light that we had on the diverter before is absent. So there's much less interaction with the plasma because it's colder, and the light is more concentrated around the X point. This just shows you what we mean by attached and detached. And it corresponds very well with the probe measurements that we saw. So electron temperature and ion temperature in the second shot are very low. And on the left-hand side, they're very high. Okay, we're starting to get some correlations. Now, so we have now the what we call the X-point radiator regime. This is it's a regime that again is kind of like a detachment, but we get it by injecting nitrogen into the machine, which leads to a sort of condensation of the plasma from the diverter. What happens is it cools dramatically and very quickly in less than a microsecond. It's a bifurcation. It's a proper bifurcation, I believe. And then all the radiation and the plasma goes up to the X point. And then it sits there radiating, and there's almost no heat or particle flux to the diverter anymore. There's still some, but it's not as high. And this is actually seen as a favorable regime for future reactors, if we can actually make it work all the time. Get into this XPR, and then we don't even need a diverter, the Germans are fond of saying. So this is a shot where we deliberately triggered an XPR, an X-point radiator. Again, the plasma begins detached. You can see this detached ohmic phase where again, the temperature is only a few electron volts, both for ions and for electrons. Then we go into an attached lower hybrid phase. So the power goes up nice and cleanly this time to 4 megawatts. And we actually, in this case, get an ion temperature of 70 electron volts. The electron temperature, again, is stuck around 15 electron volts, as usual. And then we trigger the XPR by injecting nitrogen. And both temperatures collapse down to the EV level again. So that's why we say that XPRs behave as during ohmic detachment during startup. Now we're almost to the end here. This is a compilation of all the measurements that we got by this date. So in February 2025, we got a few more in the following weeks. But we can now see distinct regimes of operation. And what I'm showing on the abscissa is the electron temperature measured by Langmuir probes, and the ion temperature on the ordinate measured by the retarding field analyzer. Now, all these points with color are discharges with lower hybrid heating. So we're going from about 1.5 up to a little bit more than 4 megawatts. And that's indicated on each point by the color. All the discharges with ohmic heating only are shown as black stars. So we can see two families here. The one at low temperatures, where both ion and electron temperature are low, is either the ohmic detached or the shots with the X-point radiator and lower hybrid heating. So we see there's two red points that I had in the database at that time. I have more points that I could show, but the result is basically the same. And then we have the same also with the LH attached. High ion temperature. So we have a cloud here of points that are ohmic attached regime. So no heating, always around 50 electron volts. There's more variation with power. The ion temperature goes from about maybe 40 up to maximum 100 electron volts for particular discharges. There doesn't seem to be much correlation with the power level. One would maybe like to see that when you put more power, you get hotter ions in the diverter. But no, we don't have any such correlation yet. So that's why I said earlier, maybe it's related to the quality of the confinement. But we haven't started looking at this yet. It's just something we would like to try to do. Now we have one oddball point here, which doesn't belong to either family. This particular shot number, and I believe I talked about it here. So it seems that maybe intermediate regimes are possible. We could call it maybe semi-detached or semi-XPR. But this is a shot without nitrogen injection at the startup, because we sometimes inject nitrogen at the startup phase also to avoid the detachment. And the session leader says this is a goodish pulse XPR formation during nitrogen ramp up, but then the feedback on nitrogen goes unstable. The gain of 2 is probably too large. Okay. You can see where things start to go crazy towards the end of the shot. There's big oscillations in the density and then a disruption. This is maybe some huge nasty MHD mode that starts up. I don't know. Related to the feedback. And so there's points where we have ion temperature at about 20 electron volts. The electron temperature itself rises a bit in this phase, but not above 10 electron volts. So we call it an oddball. So maybe we'll see it again someday on a future discharge. Maybe not. I don't know. But it seems there can be kind of hybrid regimes that occur. This one is nice. Yes. So the day I made this presentation on February 27th, fresh results from the control room. And the day before, we had a special treat. As I showed, this retarding field analyzer moves quickly. It's only in the plasma for 50 to 100 milliseconds in order to stop it from melting. And what I'm showing here is the collector current measured by the RFA in blue as a function of time. It varies because we are changing the voltage on the grids. So we apply maximum voltage. Well, when we have 0 volts on the grid, we have the maximum current because all the ions go through the grids and are collected. And then it starts to decay exponentially as we ramp the voltage up to about 300 volts in this case. And then then we have the XPR transition shown in pink here. We see a qualitative change in the data. The slope on a log scale becomes much steeper, which implies colder ions. Even plasma turbulence seems to go down a bit. We can't see it here, but if you zoom in, you can see that the turbulence is strongly reduced after the XPR kicks in. And if we plot the measured collector current as a function of the, oh, I should bring back my little laser here. Yeah. As a function of the applied voltage, this is the measurement. This is what when we say we measure ion temperature, this is what we're doing. So we like, for example, I averaged all the points as a function of voltage for these two curves here, and I plot the current versus the voltage, and we fit an exponential simply to a part of the curve. And this is what gives the one with 57 electron volts. And then after when we're in XPR, we have 22 electron volts. So this is actually nice because it gives us an indication of the time scale of the transition. And we can, from the data, just by looking at it and seeing the turbulence measurements, we could say that it's certainly less than 1 millisecond, which is going to be important for whoever tries to model this physics of this bifurcation. We have other measurements from a previous year using Langmuir probes where it's much clearer, and we could conclude there that the transition can be less than 1 microsecond. This is a paper that's being published by Federica Causa, hopefully soon, who collaborates with us. Now, I think there's nothing else here. Yeah, now we can come to the end. So the new this new probe, which was provided in kind by the Bulgarian Academy of Sciences, is starting to provide valuable new information on ion temperature at the lower outer diverter of West. We've done some dedicated experiments in the winter, so we're scanning the position of the strike point on the diverter to get different measurement points in the scrape-off layer, so to measure the decay length of the ion temperature, and some density scans, power scans, and we're over the summer going to start trying to assemble this in a clear way. So in the attached regime, with or without heating, we see that the ion temperature to electron temperature ratio is in the range of 3 to 6, whereas we always expected it should be about 1, based on hand-waving arguments, let's say. In detached or the XPR regime, the ratio drops to about 1 or 2. So there are regimes where the ion temperature can be like the electron temperature, but we don't yet really know why, because the densities are similar. The fluxes are similar. Why should the temperatures be so different in the attached regime? So we did these dedicated experiments after this presentation that I made. I haven't yet prepared the results from this. For the next campaign this fall, we are adding a new reciprocating retarding field analyzer to the top of the machine. So we will have profiles of ion temperature in the scrape-off layer simultaneously with the measurements on the diverter. There's an important question is are we going to measure 50 electron volts also in the middle of the scrape-off layer, far from the targets? We don't know, and we need to know. Now, I can say that in Tor Supra, so back in the years 2006, 2009, we had a thesis student, my first thesis student, Martin Kochan, who was making measurements with this type of probe. So ion temperatures at the top of the machine inside the scrape-off layer. And he found that, yes, the ion temperature is high, very high in the scrape-off layer. At that time, we didn't have any measurements on the limiter. So we only knew the ion temperature in the scrape-off layer. And these values are extremely typical of what you saw in a circular tokamak with no diverter. But the same heating power, so lower hybrid, also with ion cyclotron heating. He saw ratios from about 2 in ohmic plasmas up to about 10 in heated plasmas. And there was no difference in the type of heating, whether you put ion cyclotron resonance heating or lower hybrid heating. There's no difference in terms of what the ions would see. Now, another result from that, those measurements was that, again, the electron temperature was always rather low and didn't move very much with heating power. It was always stuck at 20 or 30 electron volts, while the ion temperature goes all over the map. It responds. It seems that the ion temperature responds to the core plasma, whereas the electrons don't. If you, for example, inject some impurities and the radiated power increases a factor of 2, the ion temperature goes down a factor of 2. This is what we used to see in Toshiba. But now we're going to have, for the first time, simultaneous measurements in an X point configuration at the top of the machine, so in the middle of the scrape-off layer, and on the diverter. And this probe is now being built, and we're hoping to be able to install it in September. Let's say that's what we promised anyway. I think we're on schedule, and that should be it, I think.